Radioactivity is a term coined by Marie Curie. She discovered radium and polonium and was the first woman to be awarded a Nobel Prize. She was also the fourth woman to be awarded a Nobel Prize, the only person to have received 2 Nobel Prizes in the sciences. Incidentally, she also raised the 8th female laureate, another chemist who discovered methods to create radioactive isotopes from stable nuclei. The Curies studied ionizing radiation and the radioactive isotopes that produce it. These are particles or photons with enough energy to break chemical bonds, create ions. There is, of course, non-ionizing radiation too. We're surrounded by it. It's the light coming off your screen, the heat coming off of your CPU, the Wi-Fi signal in the air. None of these forms of radiation have enough energy to interact with matter strongly enough to dislodge an electron. When radioactive isotopes decay, they move from a higher to a lower energy state and release that energy as radiation, either a particle or a photon. Now, which process it goes through depends on the isotope itself. Atoms become less stable with more protons, so super heavy atoms gain the most stability the most quickly by shedding mass. They do this by emitting an alpha particle, 2 neutrons and 2 protons, what you might also recognize as a helium nucleus. That's why we get helium from mining, even though it's lighter than air. The helium we have on Earth is a product of decaying heavy radioactive elements like uranium. Alpha particles are large and heavy enough that contact with particles in the air is enough to slow them down, and a piece of paper or your clothing or even your skin is enough to block them from entering your body and doing damage. However, if the source is already inside your body, then there's nothing to block that fatal dose.
We've traced the call. It's coming from inside the house. Squad cars on the way over there right now. Just get out of that house.
Polonium-210 is a good example of decay by alpha emission, and also a good reminder not to eat radioactive isotopes. This is how Russian spies killed British agent Alexander Litvinenko in 2006. He drank a tea they had contaminated with polonium-210 and succumbed to radiation poisoning 3 weeks later. Even though the assassins left traces of polonium all through London and in their hotel room, as long as it was external, it couldn't do nearly as much harm. Next is beta decay. A beta particle is just an electron that's ejected from the nucleus when a neutron turns into a proton. This process can help bring the ratio of protons and neutrons closer to that ideal 1-to-1. Tritium is a beta emitter. We used to use it in compasses and rifle sights to make important parts phosphorescent and visible in the dark. Notice in this equation that the mass number doesn't change and the number of protons rises by 1. That's because the electrons don't really take away any of the relative mass, and they count as a -1 proton. The opposite process can also occur. A proton can spontaneously transform into a neutron. Of course, it still needs the equivalent of an electron for that to occur. There are 2 sources of electrons available to a nucleus. The first is through the spontaneous generation of an electron and a positron, the electron's antimatter counterpart. A positron has the same mass as an electron but carries a positive charge. Potassium-40 emits a positron approximately 1 in every 100,000 decays. Since bananas contain around 400 milligrams of potassium, and the natural abundance of K40 is around 1%, that means that a banana releases 1 particle of antimatter every 2 hours or so. Now I know I just said not to eat radioactive isotopes, but you don't really need to worry about this one. It doesn't actually increase your exposure to radiation. After all, you contain more potassium than a banana, and around 1% of your potassium is radioactive too. You are also an antimatter generator. The second way that a proton can transform into a neutron is through K-electron capture. For this process, a proton in the nucleus steals one of the electrons in the innermost electronic orbital. Only X-rays and neutrinos are released. The last type of ionizing radiation that we're going to talk about isn't a particle at all, but a high-energy photon called a gamma ray. A gamma photon isn't created directly from a particle turning from one type into another, so we don't really have special equation rules for it. Instead, gamma radiation is produced when a decay process leaves the remaining protons and neutrons in such a state of disarray that the nucleus conformation is at a higher energy state. It's when it drops to its lower energy state or relaxes into a more ordered configuration that it releases that extra energy as a gamma ray. You can imagine it like a bunch of rocks held up somehow against gravity. When they fall, they become more stable. They release their potential energy as mechanical energy and sound. It's the same for nuclei, except that the energy they release is so great and so concentrated that it takes a few inches of lead to stop it. The practical reality of it is that you can't study or work with radioactivity without understanding its value, but also its risks to human health. Ultimately, both Marie and Irene Curie died of exposure to radiation, but we're living longer and better today because of the work that they did then. The safety of radiation workers remains a key priority. In fact, health physics is an entire field dedicated to the practice of measurement and prevention of exposure to radiation. We'll make nuclear applications and health physics the focus of next week's discussion.